ever wondered how a machine actually learns to make a prediction? How does it decide if an email is junk or if you should probably grab an umbrella on your way out? Well, today, we're going to find out by building a prediction machine right from scratch. Because when you think about it, a lot of really complex predictions, they just boil down to a simple choice, right? A yes or a no. In the world of machine learning, we call this classification, and it's one of the most important ideas we're going to explore. So let's do it. We're going to go on a little journey here, starting with the absolute simplest guess you can imagine, and then leveling up our model step by step. And by the end, you'll see how we can build a surprisingly smart machine that basically thinks like a flowchart. Okay, so first things first. Before we can get to anything too complicated, we've got to nail down the absolute basics of predicting these simple categories. So what is our actual goal here? The fancy term for it is classification. And it's not about predicting a number, it's about predicting a category. We're trying to assign a label, like junk or not junk. We're essentially teaching the machine how to put things into the right buckets. Now, it's really important to draw a clear line in the sand here. Classification, which is what we're doing today, predicts a category, yes or no. The other side of the coin is called regression, and that's all about predicting a specific number, like what the exact temperature will be tomorrow. For our purposes, we're sticking to categories, and we'll measure how good we are with a simple score, accuracy. To build any predictor, you need data. And this little weather data set here is going to be our playground. It's simple, which is actually perfect for what we're doing. We've got 4 factors, what we call predictors: outlook, temperature, humidity, and whether it's windy. Our mission is to use those predictors to predict that last column, play. So this little table, this is the fuel for every single model we're about to build. All right, time to jump in. Level 1. We're building our very first model. It's called the zero rule, or 0R. And it's going to give us a baseline, a starting score that any of our fancier models will have to beat. So the 0R method, the R stands for rule, and it's called 0R because it basically uses 0 rules. I'm serious. It completely ignores all that useful weather data we have. The outlook, the temp, humidity, doesn't care. Instead, it just makes its prediction by asking one super simple question: what happened most often in the past? To figure that out, we literally just count the yeses and nos answers in our play column. Yes showed up 9 times, and no only showed up 5 times. So, the most frequent class, the majority vote, is clearly yes. And that's it. That is our entire model. The rule is just this. No matter what the weather is tomorrow, a perfect sunny day, a blizzard, doesn't matter, this model will always predict, yes, we'll play. It's about as blunt as you can get, but it gives us our starting point. So here's the crucial question. How well does this, let's be honest, kind of lazy approach actually do? Well, by always guessing yes, it was right 9 out of the 14 times in our data set. That gives us an accuracy of 64%. This is our baseline. Any model we build from now on has to do better than 64% for us to even call it an improvement. We can absolutely do better than 64%. So it's time to level up and build a smarter model. Let's see if we can find the one single rule that gives us the best shot at being right. Okay, now this is a huge step up. The 1R, or one rule method, is way smarter because it actually looks at our data. It asks a really powerful question. If I could only use one piece of information, outlook, temperature, humidity, or windy, which one would help me make the best predictions? So here's how it works. The algorithm basically creates a little mini model for each of our 4 predictors. It'll test a rule based only on outlook, then it throws that away and tries one based only on temperature, and so on. And at the very end, it just picks the champion, the one rule that made the fewest mistakes. Let's see what that actually looks like for the outlook predictor. The machine groups up all the sunny days and sees that no was the most common answer. For overcast days, it was yes every single time. And for rainy days, yes was the winner. Now, it's not perfect. You can see the errors right there, but the machine does this exact same test for every single one of our predictors. So after testing all 4, we have a winner. Outlook. It turns out that if you could only know one thing about the weather, knowing the outlook gives you the most accurate predictions. So our new, upgraded model is just this simple set of rules. And the results? Just by using this one rule based on outlook, our accuracy jumps from 64% all the way up to 71%. We've done it. We've officially beaten our baseline. Our machine is getting smarter. And this right here, this is that perfect aha moment. Just by finding the single most important clue in our data, we've made a really solid improvement. We went from a totally blind guess to an informed one, and that, right there, is the heart of machine learning.
But hey, why stop with just one rule? What if we could use all the information we have? It's time to level up again and start thinking about weighing the probabilities of everything.
This brings us to a super popular and powerful method called naive Bayes. It uses probability to make its guess, but it has this one big, kind of funny assumption, and that's where the naive part comes in. It assumes that all our predictors, outlook, temp, humidity, and windy, are completely independent of each other. Now, we know in the real world that's not quite true, right? But making this simple assumption makes the math way easier. And, surprise, it works incredibly well. So how does this actually play out? Well, imagine we have a new day. The algorithm calculates two competing scores. First, it calculates the likelihood of yes by multiplying together all the probabilities for each weather condition based on all the past days we said yes. Then it does the exact same calculation for no. Whichever score turns out to be higher wins. And in this case, the likelihood for yes just edges it out. So the prediction is yes. Okay, we've gone from a blind guess to a single rule to weighing all the probabilities. For our final level up, let's organize all of this logic into a really elegant flow chart, what we call a decision tree. A decision tree is pretty much exactly what it sounds like. It's a flow chart for making a choice. You start at the very top with the root node, which is just the single best question to ask first. The answers to that question take you down different branches, and eventually you hit a leaf node, which gives you the final answer. That's the prediction. And here it is, our final, fully trained decision tree. It's this beautiful piece of logic built completely from our data. It starts by asking about the outlook. If it's overcast, the answer's yes, done. But if it's sunny, it needs more info, so it asks a follow-up question. Is it windy? See? It's a smart, efficient flowchart that combines multiple rules together. We've come a really long way from just guessing yes every single time. So there you have it. We've built our way up from the 0R simple guess to the 1R single best clue, to weighing all the probabilities with naive Bayes, and finally to this logical flowchart of a decision tree. Each step added a new layer of complexity, but it also added power. And that's the fundamental trade-off you see all the time in machine learning. So I'll leave you with this question. For tomorrow's prediction, which would you trust? The simple, easy-to-understand rule, or the more complex and maybe more accurate flowchart?